Welcome back to our final video in the series here, where we're going to finish off our section on gravity. This comes from Unit 3, Queensland Physics Syllabus. We're talking about Kepler's laws today, and he's got 3 laws of planetary motion. Have a look at that TV down the bottom corner there. Those things used to be awesome. Rightio, Kepler, who is he? He's a dead white guy? That's right. So he lived a little while ago, basically when people still were thinking that everything revolved around the Earth. Kepler was a fairly brilliant character. Now, he had a mentor, or a bloke that he worked with, Tycho Brahe, I can't pronounce his name. And basically, Tycho was a very well-known physicist and astronomer and was really the well-known one. Now, Kepler was a fairly brilliant bloke and who said, look, I'm going to work with you and work with some of your data. And Tycho said, oh, look here, just use this data here, thinking that it was rubbish data because basically he didn't want to lose the limelight to this little upstart Kepler character. But it turns out that Kepler proved some amazing things, which are these 3 laws that we still talk about today. You can have a look at those videos that I've got linked there. Now, essentially, what Kepler came up with, this data that Tycho thought was just rubbish data, was actually really brilliant stuff around how planets orbit around the sun. Now, Kepler was dealing with how planets orbit around our sun, but we've found that these laws apply to all solar systems that we've come across. So, back to our curriculum. What are we dealing with? We're going to talk about Kepler's 3 laws of planetary motion. We're going to come back to how we start to relate this back to forces of gravity, and there's a little calculation that we're going to deal with our formula down there. So, we're going to look at Kepler's 3 laws. We can solve problems, so calculations involving the 3rd law, but you will have to know all of these laws for your external exam. So, Kepler's laws of planetary motion tell us how orbits of objects orbit around some sort of larger mass, all right? And it's the larger mass thing that makes all this happen. So, the planets of the solar system, asteroids that orbit the sun. Whilst this describes solar systems very well, not necessarily how a solar system orbits a galaxy or how galaxies may move, all right? The reason it works well with solar systems is because we tend to have more than 99% of the mass of a solar system in the star that everything's orbiting around. And that's how it works in our solar system. Of that little 0.5% that's left there, the largest planet, Jupiter, is was around about 90% at least of that 0.5% that's left. So of the 5 to 10% that's left, of the 0.5% is every other planet, every asteroid, everything else, the moon, the whole lot. It's quite unusual. More than 99% of the mass of the entire solar system that we live in is the sun. Of that 0.5% that's left, more than 90% of it is the largest planet, Jupiter. Okay, Kepler's laws. We've got 3 laws that we're going to deal with. We've got the law of orbits, the law of areas, and the law of periods. They're the 3 that you need to know. Let's drill down into them. Now, our little infographic is going to appear up the top corner here as we start stepping through them. So, first one, the law of orbits. All planets orbit the sun in elliptical orbits. When we orbit in an ellipse, so like a big oval shape, we tend to have 2 foci that the oval operates around. Unlike a circle that's just got one center, we have 2 foci here. Now, the mass that we're orbiting around, which is the sun, is going to be at one of those foci that we're orbiting. So, to us, it pretty much looks like a circle, but the reality is the difference between when we're closest to the sun, perihelion, versus furthest from the sun is only about 5 million Ks, and over the whole orbit of the Earth, it's not much. It's about a 1.5% difference, all right? So if we have a circle of radius 100 centimeters around, say, U, the orbit of Earth is really only varying by 1.5 centimeters. It's very close to a circle. That's why people used to think that planets orbited in perfect circles. They're the heavens, they're perfect. But the reality is Kepler found that they're ellipses, and the sun is at one of the foci of that ellipse, even though it really looks, for most parts, like a circle to us. All right, second law, the law of areas. So basically, when a planet like this one here, is orbiting around the sun. What we have is we have the distance where we're really, really close. The planet is close to the sun, so its velocity speeds up. And when we're further away from the sun, the velocity slows down. All right. So close to the sun, the short distance away from the sun, we have a higher speed, is equivalent to a slower speed further out. And when we draw these radiuses here that I've done in the blue here, or our lovely textbook author Richard Walding has done for me, those areas, the two blue areas that we've done there, that we've shaded, are the same areas. So what I'm saying by this law of areas is the planet will sweep out the same area in the same time period. So it takes the planet getting from R to S the same amount of time as it takes to get from L to M. That's what I mean about here. It slows down, and here it speeds up. And this radius vector that we're sweeping out in areas is going to be the same area in the same period of time. That's what we mean by that. So law of areas, a planet will sweep out the same area in the same period of time. So this basically what we're talking about here is this law of velocity of increasing as we get closer is the effect that we use with spacecraft. So when we get close to large objects, the force of gravity starts to increase. It accelerates an object towards it, and we use this principle to make spacecraft go faster and faster and faster. It's called this gravitational slingshot. So here's an example of, it was a Voyager spacecraft, I think it was, going around a large planet. As the object here gets closer and closer and closer, gravity increases, it accelerates, and it bends around the object and then speeds up. So the gravitational attraction of the planet is effectively transferring momentum to the spacecraft. Think of momentum, mass times velocity. So what's actually happening here is some of the velocity of the planet is transferred to the spacecraft, but we're talking about a momentum thing. So P equals mv. Now, we're talking about a velocity increase here, but it's effectively a change in momentum that we're dealing with, all right, which is this change in velocity. But the change in momentum for a very small mass of a spacecraft of a couple hundred kilos is significant. So Voyager 1 here, it says accelerated by about 10 kilometers per second when it went past Jupiter in a gravity assist. So Jupiter slowed down its momentum, but because its mass is so huge, the velocity change is so ridiculously insignificant, it doesn't matter. So we're using the mass, the velocity of the object, the planet, to speed up our spacecraft, so we don't have to carry extra fuel to make the spacecraft speed up. Righto, the third one, the law of periods, or this harmonic law. It's a formula. Basically, this formula is simple, is t squared over r cubed is constant, as in the ratio of the period squared of an object, like a planet, divided by the radius, distance from the sun cubed, will always equal the same amount for a solar system. All right? So we're orbiting some common mass, so I can say that t squared over r cubed for the first object A is the same as the second object B. It will always give us the same amount. All right? Let's look at an example of what I mean there. So confirm that Earth and Mercury orbit the same star. If we orbit the same star, t squared over r cubed will be the same value for both of us. So I've got the period for Earth. We should know that one. How far the Earth is from the sun. Mercury is 88 days is its year, and it's much, much closer to the sun than we are. All right. Now in this scenario, we can use days and kilometers in this. We don't have to use standard units in this example. It's one of the very few examples. One of the other few examples you'll see is when we start talking about special relativity and light years and velocities in terms of a fraction of the speed of light. This is another example where we don't need standard units. All right, what do we got? So for Earth, t squared over r cubed is what we're going to work out. So I plug my numbers in there, put it in the calculator, and it all comes out in the wash there. And I get this value of 3.95 by 10 to the negative 20. I do the same for Mercury over here, and I get pretty much the same number. And we should get about the same number for objects orbiting the same object, which is the sun. So because they're the same number, our conclusion here is thus the Earth and Mercury orbiting the same star, which obviously is advantageous for us. Right, let's look at an artificial satellite orbiting Earth. All right, so when we stick a satellite up into space, how do we know how far away to put this thing and how fast it's got to be going for it to stay up there? These are the sorts of calculations that will tell us this. So satellites launched into orbit around Earth. So knowing that the natural satellite of Earth, which is the moon, has a period of 28 days, so there's my T, has a radius of R, calculate the desired orbital radius for an artificial satellite that has a period of 1 day. So if we want it to orbit the Earth in 1 day, how far away is it got to go? We do exactly the same calculation we did before, T squared over R cubed. So here's all my unknowns. I'm saying that the T squared over R cubed for the moon has got to equal the satellite. That's the M and the S there. Rearrange because I want to know how far away the satellite's got to be. Put our numbers in. That's our mathematical reasoning there. And we get this dude here, but we've got to work out our R cubed. So we've got to take the cube root of that one. So the R cubed, see how we've just got R, the radius of the satellite now. How far away is the satellite? Is 4.2 by 10 to the 7 meters or 42,000 kilometers. So the orbital radius of this satellite's got to be 42,000 kilometers. Now, question here, what's significant about the orbit of this satellite? If this satellite is orbiting the Earth in a period of 1 day, the Earth is rotating in 1 day, it means this satellite will always point at the same part of Earth. So if we stick it up in space and put it above the equator at 42,000 kilometers away, it will always point at the same point on the equator, which is effectively that same side of Earth it's always pointing at. This is really good for a communication satellite, like a satellite TV type thing that used to be quite popular before the advent of the internet. It's good for internet connections, to have a reliable connection to a satellite that's always out there pointing at you at the same part of space. Obviously, the only difference here is the light signal traveling at 3 by 10 to the 8 has got to go out 42,000 kilometers and then come back 42,000 kilometers to the server, and then the signal's got to come back to you again to load up your web page, which is a noticeable time lag. Something like an optical fiber can do this much quicker because you're not traveling 42,000 kilometers out and back into space again. Here's a nice little animation there. It's not working. I'm going to delete that. Here's a nice little animation of Saturn appearing around the moon. It's got nothing to do with what we're talking about. It's just a nice little animation to look at what happens in our solar system. Doesn't that look lovely? Absolutely. Right. Think about how we can combine Kepler's third law and Newton's third law, right? So what I haven't sort of explicitly stated here is that T squared over R cubed is a constant number for every planetary system, every solar system. What's causing this? What causes the centrifugal acceleration and the centrifugal force of an object that is in circular motion? It is the object that's moving around. It is the mass or the force of gravity of that object that is rotating around, that is so much bigger than itself. So with a little bit of fancy maths, if you'd like to drill into this, you can look it up online. But essentially what we can do is we can pull Newton's gravity formula into this and show that T squared over R cubed equals 4 pi squared over big G and then the mass that we're orbiting around. So this 4 pi squared over GM is effectively the constant value for that planetary system because it depends on the mass of the object that we're orbiting around. How much of the mass of our solar system is in the sun? 99.5%. That's why that mass is significant compared to everything else. So I've got my T squared over R cubed for my two objects is going to equal that, and that's like my constant. Now in this scenario, I am using big G. Do not forget that has units attached, so we must be back to our standard units of the metric system here. So knowing the orbit of the Earth, determine the mass of the Sun. So we know that the Earth orbits in 365 days, which is a fairly large number of seconds. And we know that how far the Earth is away in meters from the Sun. Let's use our formula on the previous slide. Our T squared over R cubed equals our 4 pi squared over GM. So from our formula here, what we're doing is we're going to start to rearrange it. So we've taken now t squared over r cubed equals 4 pi squared over gm. This guy's got to go over the other side. The r squared's got to go over the other side. There's my middle school algebra right there. But what am I interested in? The mass of the sun, which is that m there. So everything else has got to come back over this side. So the gt squared comes over here. I know my distance the Earth is away, which I've plugged into there. All the rest of it is, for the most part, there's numbers there that we're putting in. Plug it all in there. And what do we work out? The mass of the sun is 2.01 by 10 to the 30 kilograms, which is quite a lot. If we look at our formula book, we get a very, very close number to what our data book tells us it should be. All right. I do recommend checking out some videos like this guy here. Nice little way of solving some straightforward Kepler's problems. Very, very simple ones that you will end up having to do in your external exam. Might be an idea to have a pause and look at that little XKCD cartoon about the habitable zone of a fire. Now, we should understand that these laws aren't perfect. All right. We're tending to think about massless bodies in orbit, but it's a good enough approximation. Think about we've just been talking about the Earth moving around the sun, but there are other asteroids, there are moons, a moon of the sun of Earth, for example. There are other planets like Jupiter that are in the same sort of proximity in the same solar system that are going to affect what's going on here. All right. So also understand that the Earth and the sun orbit a point that is the center of mass of the two, which is not the center of mass of the sun. Think of the sun here with its center of mass. Here's the Earth some distance away with its center of mass. If we combine those two center of masses, it's going to be somewhere in the middle. It turns out that that point is inside the diameter of the sun, but it's not the center of mass of the sun that we're actually orbiting, which just gives us slight variations like we just saw in that calculation about the mass of the sun. All right. Also understand that there's differences in how we can calculate what a year actually is, whether we're referring to seasons of the calendar or pointing the same side towards the sun or the orientation of the stars in the night sky, that sort of thing, and how that lines up. There's different ways of working out how long an actual year is. Right, that brings us to the end of what we want to talk about. Don't forget, we've got 3 laws. Do you need to know them? Absolutely, you need to be able to recite the 3 of them. Do you need to be able to do the calculations? Absolutely. Do not forget, t squared over r cubed is constant for any planetary system, any solar system, because it depends on the mass of the large object, which is the sun. That brings us to the end of our syllabus sections here. And we've done all our formulas. So from here, you need to do some check your learning questions to practice this and to do some chapter reviews and so on and topic reviews. Now, one more thing. I just want to talk to you a little bit longer and get super duper technical about an extension here. Now, a galaxy is going to rotate according to the principles of circular motion. First and foremost, what actually causes this? It's the mass operating around. The mass of the galaxy is dominated by a central mass, whilst in most galaxies, this is the supermassive black hole. Like ours is Sagittarius A, we call it, at the center of our galaxy. All right, and we understand that most galaxies have this large black hole. That is the mass that we are orbiting around. All right, so let's think about how we can think about this in terms of a velocity. We're talking a force of gravity being equal to a centrifugal force. All right, so in our galaxy here, the force of gravity of this supermassive black hole in the middle has got to equal the centrifugal force to keep us in nice motion around it. So let's just move everything up a bit. So what we want to start to think about is what is the escape velocity of a galaxy, all right? So in this scenario, I've subbed in my values here, all right, where we're showing that on the left-hand side is gravity, on the right-hand side is the centrifugal force. And we want to know what is this velocity here that we need to exceed in order to get out of a galaxy. All right, and then what would this graph actually look like is what we want to actually end up doing. So if I rearrange this formula here, I end up with that one there, where as my radius increases, my velocity should start to decrease. Think about if the bottom of a fraction gets bigger and bigger and bigger, then the value of that fraction gets smaller. So we expect that as we move further and further away from the galactic center, the velocity of objects should decrease. it's effectively a graph a little bit like this. All right, so our velocity should go down as the distance from the galactic center increases. That's what we expect to see according to our classical physics. Now let's drill down into this a bit more. So there's our velocity formula that we just worked out. All right. So basically we can predict what the velocity of stars around any galaxy should look like. All right. And what we predict is essentially this graph over here. Now this is a little bit weird. We've got a rotational velocity here in kilometers per second and distance from the center of the galaxy in kiloparsecs. Now for reference, a parsec is about 3 light years. A kiloparsec is obviously 1,000 of them. Our Milky Way is about 100,000 light years across, which is about there on the scale. So this is about 330,000 light years. So more than 3 times the size of the Milky Way. So we're talking quite large galaxies we can work this out for. Now the rotational velocity tends to be very much less than the speed of light. Now how can we work this out? We can work this out from basically the redshift of the wavelengths of light that we're receiving from these stars that are rotating around galaxies. Now, as a Doppler effect thing is what I mean by the redshift. As the object is rotating around, there is a Doppler effect, and we get this change in velocity compared to what the change in wavelength compared to what the original wavelength of that light was, which is the observed minus the original over the original. And what we tend to start to realize is it's a velocity over c, speed of light. We can work this out in terms of some trigonometric ratios, and we're talking really here about radians instead of degrees. I've mentioned those before in a previous video where, remember, degrees is from your point of view, how far are you going in terms of an angle theta from your point of view, whereas a radians is how far is this bit over here moving as we move around the circle. And that's what that u sine I is starting to talk about over here. Now, so we can measure the frequencies or wavelengths of light from different objects in our galaxy and others. And what we expect to see is that as the distance from the center of the galaxy increases, the velocity should decrease, because that's what this tells us here. As that r gets bigger, v gets smaller. R getting bigger means a smaller fraction, a smaller number. But that's not what we see. We see this line here. We see that as the distance from the galactic center increases, the velocity remains relatively constant, something approaching about 200 kilometers a second, which is about how fast our sun's moving around the Milky Way. So the question becomes, look at your formula. Why? If this is changing, but this is staying constant, what has to change in response to this? That's the only other variable. There must be more mass in galaxies than what we realize. So the only way a velocity increases is the distance from the center of a galaxy increases is because there's more mass in the galaxy. But we can't see or detect any of this extra mass, so therefore we call it dark matter. That's how we know that this thing called dark matter exists. This velocity is staying constant. It's not following the curve that we expect, so there must be more mass further out in galaxies that we can't see. It's not all just concentrated in the center. That's this dark matter. So now, just to take this a little bit further, if we exceed this velocity in a galaxy, that's the escape velocity. So the question becomes is where would it theoretically be easiest to leave a galaxy? Really, the further we get away from an object, the further that force of gravity to the supermassive black hole in the center should decrease. So it should be easiest to leave the galaxy from the outer edge. All right? How could this happen? This could happen when a star goes supernova and explodes out into space. It could eject its mass into space, and the galaxy could then lose mass. What's the implication of losing mass? We start forming stars less, and the galaxy starts to die. So, escape velocity is closest to the edge of a galaxy disk, because the R increases. As a star from a large star, so giant O and B class stars, so big ones, much bigger than our sun, so I think 10 to 100 times bigger than our sun, get to the end of their life and they literally collapse on themselves and explode out into space as a supernova, and they eject a lot of their mass out at a very high velocity. But these stars tend to form where there tends to be more matter that we can see in galaxies, which tends to be closer to the center of the galaxy. So smaller galaxies, the ones that have lower mass, tend to lose mass because the bigger galaxies tend to have mass to attract that gas back into itself. Let me explain what I mean by that. Look at this little scenario here. We have a galaxy disk here, which is this blue disk. We have a star here that's gone supernova, so it blows all its matter out into space. And because it's a disk that we're talking about, a lot of that will go out following this dotted path. Now, if the velocity that goes out at is bigger than the escape velocity, the galaxy will lose that mass forever and it will never be able to form new stars, and hence it starts to lose mass and die. And a dead galaxy is one that's dormant, that's not really forming many stars. But as this mass ejects out into the area above the galactical disk, it starts to cool. Once it starts to cool, its velocity will start to decrease, and then hence it then comes back down in this cycle back into the galaxy and can then be used for more star formation. This little bit here about absorption and emission spectra is something we're going to come back to in Unit 4, where we talk about quantum physics. Anyway, that's a little bit of an extension for you about how we sort of start to use these principles in astronomy and astrophysics. There's a couple of quick videos for you. I recommend you have a check out. But we're at the end of this series, so thanks for coming. Make sure you do the practice questions. Have a look in the description below about what you need to do, and I'll see you next time. See ya.